Okay, great. So today we're going to talk about common sense reasoning in natural language processing. And we have 4 hours, so I'm going to split it to sessions. We're going to have a break in the middle, and I think we have a lot of time. I also left 30 minutes in the end for questions and discussions. In terms of any clarification questions that you have throughout, feel free to well, first of all, you can write it in the chat, and I'll do some pauses during the session to answer questions. And I'll also ask occasionally if you have any questions. So if I ask if you have any questions, feel free to just unmute yourself and ask it. Okay. So sorry. So this is going to be the schedule. So we're going to start with a short introduction of what is common sense. Then we're going to talk about Commonsense Benchmarks, which is the way that we measure progress on common sense, on researching common sense reasoning. Then we'll talk about acquiring common sense knowledge and storing it in knowledge bases for models to be able to use. Then we'll have a break. We'll come back, we'll talk about methods in common sense reasoning. Then we'll briefly talk about the reasoning part, because most of what we do is not really any kind of advanced reasoning. And as I said, we're going to have half an hour for questions in the end. All the times are in Pacific time, because that's where I'm at. So yeah, you can maybe take a screenshot if you want to see the schedule throughout the sessions. Okay, so let's start with an overview. So in the last few years in NLP, we've seen a lot of progress thanks to deep learning. So you can see that we had a lot of progress on tasks such as machine translation, reading comprehension, chatbots, and these are just examples, and these are all news headlines because apparently NLP is now something that's on the news. And if you are within the field, then you would typically track the progress with leaderboards such as Superglue. So this leaderboard involves a range of complex language understanding tasks. And I don't know if you can really see it clearly here, but it was launched in July 2019, and then about a year and a half later, human performance was already surpassed on this leaderboard. So the inevitable question is whether language understanding is already solved or nearly solved. And I'd like to argue that it's not nearly solved, and that one of the major challenges that we have is the lack of common sense reasoning abilities of these models. So just to be on the same page, I'm assuming most of the people attending this tutorial have some basic knowledge of NLP, but just to be on the same page, most of the recent success is thanks to pre-trained language models. There are two approaches, two types of them. One of them is masked language models, such as BERT, and the other one is standard or causal. I don't really like this term. Standard language model, like GPT and GPT-2 and 3. I'm not going to talk about the difference here. This is something that's shared to both of these types, that they first have this pre-training phase where they sort of like read a text corpus, large text corpus, such as the web or Wikipedia. And by reading, I mean they're trained in a self-supervised manner to predict a missing word in its context. And this pre-training step teaches them a lot about language. So they learn a lot about syntax, like what part of speech is suitable in which context, etc. It learns a lot about word meanings and some factual knowledge about the world. And then the main paradigm in NLP today is to take these pre-trained models and then continue training them or fine-tuning them on specific tasks. So for example, if you wanted to train sentiment analysis model, then you could encode the inputs such as the chocolate cake is amazing using the language model such as BERT. And then this would output a vector, which will then go into a classifier to predict positive or negative. And then typically what you would do, you would back propagate the error to update both the classifier and the language model itself. So you get a BERT representation that is trained to do sentiment analysis. And then this fine-tuning step is responsible for both understanding the task and also learning to solve it, or more technically, learning this mapping between the input and the output. And we have some generalization issue here. So when you look under the hood of these models, it seems that the accuracy of such models is a bit misleading. And this is something that has been shown for various supervised models, not just in NLP and not just transformer-based models, that they tend to learn dataset-specific spurious correlations instead of actually solving the underlying task. And I'm going to show an example, which is actually before the transformers. It's using a different architecture, but it's just because it's the most intuitive example. So this is a visual question answering model that learned that when it sees a question that starts with how many, it just outputs 2, regardless of the image. It doesn't even have to look at the image. Just based on the text features, it answers 2, because most of the images in the training set that asked about how many something are there, their gold standard answer was 2. And it's pretty common actually that these things, this is kind of overfitting. But I don't know how it is today, but when I learned a basic course in machine learning, I learned that if a model overfits, it gets good performance on the training set, and then it's penalized on the test set. So you can see that when you get the performance on the test set. But in practice, many of these test sets are built in a very similar manner to the training set. So they have a very similar distribution. So you could potentially get really good performance on these tasks without actually solving the task. And that's very common today in many tasks. So the bottom line here is that these models, they often learn to solve the data sets that they were trained on without actually solving the underlying tasks, or without properly solving the underlying tasks. And this is in contrast to humans, and I'm going to get a bit hand wavy here because I'm not a cognitive scientist, but humans are pretty good at generalizing from very few examples and then handling new data. So for example, if you show a child a picture of a cat and say something like the cat eats, then this child might learn this abstract representation of a cat. And then upon seeing the cat doing other activities, they can say the cat drinks or the cat sleeps, or seeing a slightly different cat doing similar activities, they can still recognize it's a cat and that the cat is eating. And this is very different from neural networks, because you need to actually show them a lot of different examples that are similar in order for them to be able to generalize. So how is all of this related to common sense reasoning? So as long as machine learning is the dominant paradigm in NLP, and I think it's probably going to stay this way for a while, we can only train models on a sample of the situations that they would encounter in practice during inference time. And so if we want them to be able to address unknown situations reasonably, then they probably, one way to do that would be to teach them common sense reasoning, knowledge and reasoning abilities. And specifically, there are 2 properties of natural language that especially call for that. One of them is that natural language is sometimes ambiguous. This is the headline from the news from about 2 years ago. It says, Stevie Wonder announces he'll be having kidney surgery during London concert. Now, when I say it's ambiguous, I think it's so easy for us to interpret the meaning of this sentence that it's almost hard to see what's ambiguous about this. But let's say that I ask the question, when is the surgery? You would know to tell me that the surgery is sometimes after the concert and that the announcement happened during the concert. This answer during London concert is from a state-of-the-art QA model, a model that's very large and that's trained on 20 QA data sets. So even the best models make this mistake. The reason that we know how to interpret this sentence correctly is because we can reason about our knowledge. For example, that kidney surgery is performed under general anesthesia, that people are unconscious under general anesthesia, and that performing actions require being conscious. Here's another example. Another property of language is that it's often underspecified. So we don't say everything we know because we only say what we assume to be complementary to the listener's knowledge. And so there are sometimes phrases that have some kind of implicit meaning, like grass-fed yogurt. Something like that means probably means yogurt made of milk from grass-fed cows. And the reason that I know that is because I know that yogurt is typically made of cow milk, and that it could be made out of different milks, like goat milk, for example, but it would probably be specified because cow milk is probably the default here, and that cows eat grass, but that yogurt is an inanimate object, so it can't eat grass. Yet when you use, for example, Google Translate to translate this phrase to a language that doesn't have this equivalent phrase with this implicit meaning, it sometimes gets it wrong. So here it was translated to Hebrew, and the equivalent of the translation would be something like yogurt with grass, which is incorrect and also pretty disgusting. So I've been talking about common sense for a few slides now, and I didn't formally define it. That's most likely because it's pretty hard to define the boundaries of common sense, but I'm gonna go with the definition that we used in the common sense tutorial we gave at ACL last year. So this is the basic level of practical knowledge and reasoning concerning everyday situations and events that are commonly shared among most people. So that includes, for example, physical common sense, such as knowing that it's a bad idea to put your hand on top of a hot stove. Social common sense, such as knowing that it's impolite to comment on someone's weight. Temporal common sense, such as knowing the typical times and frequencies and durations of events, such as, for example, that dinner comes before going to bed. And many other things could be considered common sense. So this is essential for us humans to live and interact with each other in a reasonable and safe way. And it's essential for AI to understand human needs and actions better. So let's talk a little bit about the history of AI. And now I'm not talking specifically about, the history of common sense, and it's not specifically in NLP, but more broadly in AI. So starting in 1956, there was a workshop at Dartmouth that was organized by John McCarthy, where AI was established as a field. And it's like an anecdote I like about this, is that they had in the proposal, they were talking about how in 2 months, these 10 men over there, they would solve AI, which they didn't realize how hard it's actually going to be. It just comes to show how notoriously bad computer scientists are in estimating how long it would take us to complete tasks. But they met, and this started this era, this time of about 18 years of optimism and high expectations. That also led to increased government funding. It was a really good time to do AI. You could get a lot of money to do research. At the same time, there was a lot of overclaiming, probably worse than we have now. For example, people would name their systems the general problem solver, even though it was solving very specific toy problems. And then one of the examples of a system that was developed in this time was ELIZA. And I'm going to show a video. I hope it's going to work. I think this video really demonstrates it well.
destroying my home. Thankfully, it came preloaded with a program to help solve personal problems.
Hello, I am Eliza.
My parents are fighting a lot.
I see. Can you elaborate on that?
My mother bought me this computer, but my dad says we can't afford it.
Do you have issues with your mother?
No. She makes me spaghetti with hot dogs cut up in it.
Can you elaborate on that?
Are you going to help me or not?
Hello, I am Eliza.
The future might be overrated.
Yes, so just a second. Okay. Yeah, so this was a scene from Young Sheldon, and just I think it was a very good demonstration of Eliza. So Eliza was this, it's supposed to be like a therapist, and it wasn't really intelligent in the sense of the systems that we developed today. It didn't learn to answer these questions, but instead it was just using these very templated answers and questions, like recognizing the topic and then asking, can you elaborate on that topic? Or recognizing the sentiment and saying, do you have issues with something? Something interesting about it is that people said that even though they knew they were conversing with a bot, they still felt good talking to it, probably because we just sometimes need someone to listen to us. So that was the first 18 years, and then there was a period of that's called the first AI winter, where all this overclaiming and the lack of actual progress made funding agencies stop the funding. And that was a bad time to do AI because you couldn't really get funding to do research. And specifically, some of the major problems that prevented progress were, first of all, that many of these systems were based on reasoning by searching the solution, the optimal solution, which often led to combinatorial explosion and was intractable, especially when you think about the weak compute that they had back then. In addition, there was lack of common sense knowledge and reasoning abilities. They learned that apparently to be able to perform very simple tasks, the systems needed to know a lot about the world. The fact that the systems were based on logic made them very rigid, while the real world is actually pretty messy. For example, it caught something called the frame problem, which is when you use logic to express facts about the world, you need to specify many axioms about things that are not true or things that do not change, like, for example, do not change arbitrarily from an action that the robot performs. So this is pretty hard to do, to define everything that is not true in a given situation. But other than this failure to recognize these problems or the unrealistic expectations that AI researchers back then had, much of this was not the fault of them. It was not their fault, but rather due to weak computing power and not enough data. You couldn't just scrape the web like you can do today. There was no crowdsourcing either, and the weaker computational models. And then this period of time between 1980 and 2011 could definitely be broken up to more fine-grained ranges. But in general, what I want to say about this time is that there was some progress. It was slower progress than in the last 10 years. One of the major things that were happening back then were expert systems. Those are systems that are aimed to mimic the decision-making process of a human expert. So they're typically domain-specific, and an expert would just encode the knowledge their knowledge into some knowledge base, and then these systems were not intelligent in the sense that we mean today, because they don't learn to perform any tasks, but they are programmed to perform very specific tasks using this knowledge. And then in the last 10 years, deep learning became very popular with big data. These are the two main reasons. I mean, many of the deep learning architectures and algorithms were available before that, developed by the few people that did work on that during the 80s and 90s. But it was hard to get good performance with them because the compute was too weak and there was not enough data to train on. And these two things together, the better computers and a lot of data on the web made it possible to get really good, really impressive gains in performance on many tasks. With that said, it's probably not going to take only training ever larger neural nets on more and more data to solve common sense. Well, probably will take more than that. I'm using this code. This is a slide from the ASL tutorial, and I don't know who to attribute this code to, but I like it. You don't reach the moon by making the tallest building in the world taller. So what is the path to common sense going to include? Probably at least a few of the following. First of all, benchmarks, so we can track the progress on track our progress, research progress. Also representing knowledge about the world. Then also some kind of neural representations and models, and eventually putting it all together in some reasoning engine that could use this knowledge as well. And we're going to talk about each one of these today. So I think now is the time for questions. Let me look at the chat. Okay. The ideas of Minsky and society of mind are fundamental on common sense reasoning in AI. How much impact does this have in the actual research in NLP? That's a good question. I think there's somewhat of a disconnect between or maybe it's starting to get better, but there's like an NLP community and there's an AI community, and there's some overlap, more than before, I think, in the last few years. I think there was some time that these two communities were kind of disconnected. I'm coming from the NLP background, and for example, I only attended AAAI for the first time last year, and now there's starting to be more NLP there. So I think now we're starting to share more ideas, but I think most of the NLP research, at least in the last few years that I'm more aware of, is not really. I mean, it's I say it in less like in more harsh words. I mean, we're often reinventing the wheel because we were either not aware of something that was already done, or I don't know, because things didn't work in the past, so we don't try to use it again. So yeah, I don't know. I guess the answer is that there's not a lot of work on that in NLP, unfortunately. Okay, any other questions before we move on? Oh, I think there's something else in the chat. Okay. Okay, let me move on to the second presentation. Okay. So in this part, we're going to talk about common sense benchmarks. So starting again with a little bit of history. So the Turing test is a test of intelligence that was suggested in 1950 by Alan Turing. Instead of answering the question, can machines think, he proposed to answer the question, can a human judge distinguish between a human and a machine following a short conversation with each? And then this was also, there was also a competition based on that called the Loebner Prize. It was since the 90s. I think it stopped a few years ago. In one of the years in 2014, the bot that won the competition was named Eugene Gustman, and it was simulating a 13-year-old Ukrainian boy. And it was pretty smart of them to do that because supposedly that boy didn't speak English very well. So he couldn't really have a very meaningful and deep conversation in English. And then you could have a very short and simple conversation with a bot without exposing the bot, but you can't really have like a grown-up, meaningful conversation without exposing the bot. So that's just to show that unfortunately it was pretty easy, or it was possible to cheat and win without actually having intelligence. And unfortunately, that's the situation with many tasks. If you're interested in that, I would like to recommend, first of all, there's a book called The Most Human Human. That was written by one of the humans participating in this competition. He was talking about how can I prove that I'm actually a human and not a machine. So that's pretty interesting. And there's also the blog called The Artificial Detective. That's about someone who, that's written by someone who developed chatbots for these competitions. He's actually not an NLP researcher, so he's using different methods from what I knew, so it was really interesting for me to read. This is more recent, but also almost 10 years ago. The Winograd Schema Challenge is based on a proposal by the linguist Terry Winograd, and it is a pronoun resolution task. So it's very like a special case of coreference resolution, where you have a pronoun, like in this example, the city councilman refused the demonstrators a permit because they advocated violence. And then the goal is to determine who is they. Syntactically, it can refer either to the city councilman or the demonstrators in this sentence. So you actually need common sense reasoning abilities to solve this, to resolve this this task. So for example, here the answer is the demonstrators, because it doesn't make sense that the city councilman would advocate violence. What makes this task especially difficult is that each one of these, each example like this has a twin example in which something was really minimally changed, but the answers are then reversed. So here, instead of advocated, it says feared. So now, who feared violence? The city councilman. The dataset has multiple, it exists in many languages. I recently translated it to Hebrew, but only, I think most of the considerations about building it in a hard way were mostly applied to English. One other thing they tried to do to make it difficult is to make sure that it's impossible to Google the answers, to make it not Googleable. Although if you look at the methods that have been developed for this in the last almost 10 years now, many of these methods are actually based on statistical association. So maybe you can't Google exactly that, but you can Google very similar, or you can look at the text corpus and find similar associations. Yeah, I think it's mostly because it's an old data set and it's pretty small. It has only, I think, 200 and something examples. There's no training set, and it's a bit too small at this point for quite large community to work on. So people just focus on benchmark specific hacks to solve this particular benchmark, while the task itself is not quite solved. There are many other benchmarks. This slide is from, again, the Commonsense tutorial at ACL that we gave last year. I actually mentioned it a few times, and maybe I should say many of the slides are based on that. So I would also like to credit the co-instructors who gave that tutorial with me. So this is from about a year and a half ago, or yeah, about a bit over a year ago. So there are a lot more benchmarks now. And this wasn't an exhaustive list back then either, but this is just a few examples. So you can see some benchmarks focus on specific types of knowledge, like social common sense or physical common sense or temporal common sense, while others are more broadly targeting common sense through different types of tasks, like common sense reading comprehension or other types of tasks. There's also this website where you can see it. I think it's much more up to date. You can see a lot of material about common sense in general, also specifically about benchmarks. This is a website that is developed by Bill Lin from USC. So let's talk about a few of these tasks. So the first one I want to talk about is social IQA. It is reasoning about social situations. So you have this context that talks about something that happens to a person, like Alex spilled food all over the floor and it made a huge mess. And then there's a question, and the question is about one of several aspects of the person's motivations and intents and feelings. So here, for example, it asks about what will Alex want to do next. And then there are four options. I'm showing two here. So either run around in the mess or mop up the mess. And the more likely option is that Alex will want to mop up the mess. Here's another example, physical IQA. Here is about physical common sense. So the context is the question here is some kind of goal, like separating egg whites, and a specific tool that is supposed to be in use. So, for example, using a water bottle. Again, there are two options. The more likely option is taken from WikiHow, and the less likely option is some modification of that, a small modification of that makes it nonsensical. Like if you keep pushing, then it creates suction, but if you release, it doesn't create suction. And you need to know something about physical common sense to be able to answer this correctly. COPA is a pretty famous data set. Most of the data sets that I'm showing are large, except for COPA and the Winograd Schema challenge. There are only a few hundred examples. This is slightly larger, but I think it has like 400 or 500 examples in the training set. So here there's a single sentence context, like the man broke his toe. And the question is either about what caused that or what was the effect of that. It's more likely that the cause for that was that he dropped a hammer on his foot than that he got a hole in his sock. And rock stories is also pretty popular. So this is input is a 5-sentence story, a very daily, everyday, simple story. Like Karen was assigned a roommate her first year of college. Her roommate asked her to go to a nearby city for a concert. Karen agreed happily. The show was absolutely exhilarating. And then the models need to predict out of two options, which sentence is the more plausible continuation, sorry. So it's more likely that Karen became good friends with her roommate than that she hated her roommate. This seems like a pretty easy example, and indeed this task already has, there's a very good performance on that already. So these were a few examples of a benchmark. Are there any questions before I talk about how to build a benchmark? Okay, so I'll continue. So here are some considerations when we build a new benchmark. So first of all, we need to define what it tests. Typically, you would want to focus on a specific capability. It could be a specific type of knowledge, such as social common sense or physical common sense. It could be a specific type of reasoning. We'll talk a little bit about reasoning modes in the end of this course. And and it could be more broad, like like the rock stories or Winograd Schema challenge, or targeting more a broader definition of common sense. Second is how large you want it to be and how to collect it. So this seems like two different questions, but they're actually they're dependent, because if you collect if you want to collect it from experts, then probably you're going to collect a small data set because it's time consuming and expensive, and then probably you won't have a training set. Or you could also crowdsource it, and then you could collect a larger data set and provide also a training set. And finally, how to collect wrong answers. So all the benchmarks that we saw so far are multiple choice benchmarks. So you have both the correct answer and also one or more incorrect answers, and the model needs to pick the correct answer. And so what you want out of the wrong answers is that they would be plausible, but less likely or unlikely, because you want it to be as difficult as possible, and it could be, it's not trivial to do that. Let's look at a few examples on how to do that. So first of all, the most straightforward way you could do that is if you collected only correct answers, and then you just sample, do some kind of negative sampling to get the incorrect answers from different questions. But that's too easy to detect because they're going to be topically dissimilar. So there are a few other options. So you could also ask people to write negative answers. If you crowdsource the correct answers, you can also crowdsource the incorrect answers. And this is an example from Social IQA. I think when they first collected it, they tried to do that. And so again, going back to the question about Alex, let's spill food all over the floor. What will Alex want to do next? And so they collected the correct answers, which are workers suggested to mop up or to give up and order takeout instead. And as negative or wrong answers, they suggested leave the mess and run around in the mess. It doesn't seem wrong to me. I mean, it doesn't seem bad to me. I don't know if it seems bad to you, but something about these answers is easy for models to detect without actually looking at the question or the context, because they're often too exaggerated, or they could be off topic. So just with respect to the context, they're not related enough. Some of them are sometimes overly emotional. So all of these make it too easy for the models to detect. It's actually reducing this task to an easier task of detecting something that is unrelated or too emotional or something like that. I think these examples specifically don't really show that, but I don't know. You could imagine something more dramatic, like if they suggested he will, I don't know, Alex will break more plates on the floor or something like that. Another approach is to collect these answers from crowdsourcing workers, but then filter them out and keep only the difficult ones. This is done by training simpler models. This is like done iteratively during the collection, using, for example, pre-trained representations such as BERT, and then training a simple classifier using BERT, like logistic regression or something like that, where you can expect people who actually work on this task to develop more complicated models. And then everything that this model gets correctly is too easy, so you just remove it. So you do end up with robust examples. It does make the data set much more difficult. But I personally don't think that's the best solution. I have other preferred methods, because I think this also creates a bit of artificial difficulty. But that's one way to do that. Here's another way, which is the one that I prefer. So this was actually done eventually with Social IQA. So the idea is to do kind of not negative sampling, but to use the answers of different questions, but it is for the same context. So something that's special to social IQA is that the same context, like the sentence here talking about Alex spilling food, is used for multiple questions, because they had various types of questions that they could ask about it, like what will Alex want to do next, or what did Alex need to do before this? And then what they did is taking the positive answers for what will Alex need to do before this, and then using them as the negative answers for what will Alex want to do next. And at the very basic level, it's at least related. It's not off topic. And it's also not, it doesn't have these artifacts or something that's special only to negative answers. So that makes the task a little bit more challenging. Let's have a short discussion. Maybe before we start with the discussion, let me look at the chat. Okay. Question from Sahithya. Many common sense tasks seem to be discriminative in nature. Are there any tasks which are focused on text generation? For example, the model has to reason and generate plausible sentences given some scenarios or concepts. Yes, there are. I'm actually going to talk about it in a few slides. Thanks for asking that. Okay, another question. We can keep building benchmarks targeting unsolved parts of common sense and solving the benchmarks. Do you see a limit in this approach towards finally solving the problem? That's a good question. I think that yeah, maybe I'll answer that after the discussion, because I think the discussion is somewhat going to answer that. And the last one, adversarial filtering, probably try to remove closed domain kind of question. The answer is already inside the question. I guess it would definitely remove these examples, but it's not necessarily that. To give another example, I was talking earlier about the spurious correlations. I gave the visual question answering example, but another example is in natural language inference. So there, I don't have a slide for that, but I'm just gonna try to answer it without the slide. The task is to determine whether a sentence entails or contradicts another sentence or is neutral. So something that was discovered that these models do is that if there's a negation in the sentence, like, okay, I'm going to take a step backward. So there is a very famous data set called SNLI, so Stanford Natural Language Inference corpus, that was built such that the premises are image captions. So we have all kinds of images, like a dog is running in the park. And then the hypotheses were crowdsourced from people. And so people, they were asked what is entailed by this sentence. So they would just generalize and say something like, animals are outside. And then they were also asked to provide contradicting examples. So they would say something like, a cat is running outdoors. And then one thing that there was a paper a few years ago that showed that the models that perform well on this task, they sometimes find just the existence of a cat in the hypothesis is indicative of contradiction. Because image captions contain a lot of dogs, and when you ask people to negate dogs, they just say something with cats. So that has nothing to do with inference, right? It's just modeling how people write negative examples. So it's not always very easy to detect it. That's why it's also not trivial to remove these kind of biases. Yeah. Okay, so I want to have this discussion for a few minutes. I want to ask you, what do you think are the advantages and disadvantages of these multiple choice benchmarks? I mean, not specifically the benchmarks we talked about, but in general of multiple choice benchmarks, or classification tasks also have the same issues. So let's start with the advantages. Anyone wants to say something about it?
I think it's easier to evaluate classification tasks. That's the main advantage with using them.
Definitely. Thanks. Yeah, that's the main advantage. That's probably why we're mostly working on multiple choice and classification tasks. It's just very easy to evaluate. It's automatically with accuracy or F1. Any other advantages? You can also say disadvantages if you already have ideas of that. I can see if anyone is raising their hand. Let me look. Okay, I'll give a few more and see if you have more ideas. So a few more advantages. Sorry. Oh yeah, I see a hand. Yeah, Suk or Suk.
Hi, yeah, thanks. Yeah, so maybe disadvantages would be limited choices.
Okay, interesting. Oh, okay. Yeah. So you mean
As in, like, because multiple choices, you are just given, for example, ABC, but then maybe your choice might not be in the available option.
yeah, that's a good point. So I think we're going to talk about it in a few slides. Yeah, it's more. I mean, it is expected that there is an answer, there is a choice that would be correct among those choices. But I think maybe what you're trying to say is that there could be multiple correct answers for some questions, and then the answer that the model thought about or predicted is not necessarily one of the options. Is that right?
Yeah, that's right. I
Yeah,
mean, as in, like, for example, also maybe if you wanted to choose like multiple, I guess if you wanted to choose multiple choices, like A and B might be right, but you're just limited to A, for example.
Yeah.
Or
Right.
one option, I would say. Yeah.
Yeah. There are some benchmarks that allow for more than one option. Very few actually. But yeah, it's still limited because it's from the list of options. Yeah. Thanks. I see also in the chat cultural or contextual differences. That's true. It's not necessarily an issue with multiple choices in general, but it is related to the fact that you have to have like one correct answer. We'll actually talk about it soon. And we have here, potentially we can reduce other types of problems into classification, so it may be a general way to solve the problem. Yeah, so I'm assuming that's an advantage. Yeah, I think multiple choice and classification are very similar in that aspect. It's in general like the same advantages and disadvantages of discriminative tasks in general. Yeah. And we have another raised hand. Arthi.
Yes, hi. So I think like maybe like one of the disadvantage is like try thinking to like, for example, like if the question it's maybe something like, or let's say like hypothetical one, maybe it's just like adding numbers and it's like all like even numbers, right? Maybe I don't know actually how to calculate this, but because of like you have like 4 choices and 3 of them they are odd numbers.
Yeah.
So I just crossing out all those odd numbers and pick the even number. I don't actually know how to calculate, but I probably have some like limit, like intelligence, like, well, it's not going to be the odd numbers. Will that be like kind of advantage, disadvantage?
Yeah, exactly. It is an advantage if it happens to you when you're in an exam and you can just eliminate the incorrect answers and be lucky to answer the question correctly. But it is a disadvantage if you actually try to measure if models have this capability. And that's also related to the spurious correlations that we mentioned several times, that it's actually quite easy to game these models, these tasks. And yeah, we have another raised hand, Jing.
Yeah, hi. So I think one disadvantage is that the fact that we're breaking down the answers into categorical choices itself is a common sense task that the model will not get to learn, right? So I guess
Yeah.
handicap to the model so that it cannot learn this kind of breaking down of the world from continuous chaotic patterns into categorical discrete patterns.
That's very true. Yeah, it is. Yeah, it's not nuanced like when you can. Yeah, it's a very good way to lead us to the next slide. I just want to thanks everyone for your answers. I just want to go back to the question about is there a limit to this approach of building new benchmarks and solving them? I don't know. It's hard to tell because it's. I mean, it is a good way to, so maybe I'll answer it by summarizing all the points that were raised and maybe adding something if there's anything else I thought of that wasn't mentioned. So in terms of advantages, obviously, I mean, one of the main advantages is that these tasks are easy to evaluate. It's a standardized way. If you define a benchmark, it's a standardized way to measure a particular capability, and especially if you have a leaderboard for that. It is, I'm not a fan of leaderboards, but I have to say that it makes life easy because it's an easy way to compare between systems. It's fair. You don't need to reproduce the results of previous work, which used to be very common until a few years ago. All the previous results are known. You don't need to write the evaluation code. You just submit to the leaderboard. You get your name somewhere there in the table. So all of this is the good part of it. The disadvantages are, as we mentioned, that one of them being the problem with it's actually quite possible to game the task in multiple ways without actually solving it, and that adding this kind of artificial adversarial filtering is sometimes making these tasks a bit artificial. And so this leads me to the next slide, which is somewhat related. Here we're not talking about, so yeah, actually it is the same. We're talking about, again, about the discriminative tasks as opposed to the generative tasks. So yeah, as we mentioned, they're easy to evaluate, but models are often right for the wrong reasons. And I think someone also mentioned that it's sometimes you have more variability in the answers. Sometimes there are inherent disagreements, and it's just fine because people don't necessarily agree on everything. And in discriminative tasks, you have to have like one correct answer. And then eventually these benchmarks, how good they are, depends a lot on the quality of the incorrect answers, the distractors, which sometimes makes the task a bit artificial. There is an alternative of generative tasks where the task is to generate an answer in free text. And it's better in many ways because it allows for a more nuanced and flexible reasoning than when you predefine the labels or the answers. It is much more similar to the way that we reason because we're not typically provided with candidate answers. We have to come up with them ourselves. And it is less prone to spurious correlations or to gaming these tasks because the answer space is basically infinite. Unfortunately, for that same reason, it is much harder to evaluate these models automatically because it's hard to judge the correctness of a free text answer with some automatic evaluation metric. And to date, we don't really have a reliable automatic evaluation metric. Here's an example. We're going to talk about this task later, but this is just, I think, a pretty intuitive task, so I'm using it as an example. So here, the inputs are a past observation. For example, Sarah wanted to make dinner for some guests, and the future observation, she had to order pizza for her friends instead. And the goal is for the model to generate a plausible explanation of what happened in between. So for example, we could have a reference sentence in the data set saying something like, she realized that she doesn't know how to cook. So how do we evaluate a model that predicts a sentence like this? So we would like our metric to reward correct answers that are different from the reference. For example, we could think of an alternative explanation. For example, she did cook. but then right before the guests arrived, she tasted the food. It tasted horrible, and she didn't have time to cook anything else. So she just said, okay, I'm going to order pizza. That's a plausible answer as well, but it's very different from the reference. So if you're, you need your metric to be able to say this is correct, even though it's different from the reference. And that's probably the harder thing to do, because it's not, it almost is almost as hard as solving the task itself. On the other hand, if we also want the metric to penalize answers that are incorrect but are similar to the reference. So for example, we could say, like, if the model predicted something like she didn't know how to cook meat, then lexically it's very similar to the reference, but it is incorrect because she could cook something else. And so the metrics that we use today are either based on lexical overlap, so just n-gram overlap, like blue and rouge that are used for translation and generation. And well, first of all, it has been shown for many tasks that there's a very weak correlation between these metrics and the human judgments. And second, they by design don't really support lexical variation. So if you even predict the same answer but rephrase it slightly, then you would be penalized for by this metric. The other option is the other option is to use metrics based on semantic similarity, like BERT score, and they deal pretty well with lexical variation, but the problem is that they tend to reward answers that are similar to the reference, even if they're incorrect, even like opposites or negation, stuff like that. I think that was the end of the second session. Any questions so far? I'm going to open the third slide deck while we maybe let me just check how we are with time. Okay, we're slightly behind, but we have a lot of time for the next session, and I don't think it's going to take as much. Okay. I see a hand raised, but I think it's still raised from earlier. So let me know if you have a question. Okay. So let's continue to the third part. This is about acquiring common sense knowledge. Oh, wait, there's a question in the chat. Is there any benchmark like let the computer sort cards of stories? Oh, you mean like sorting the order of sentences in the story? I think there is
maybe something like that. It can be kind of like just like maybe you given like a set of cards and let them play, for example, like maybe like sort it by timeline, or maybe like out of it's like 5 cards, maybe like one card is like totally relevant, and in order to have like a sound story, you actually have to remove that card and have only like 4 cards.
Yeah, first of all, I think it's an interesting idea. I think there are some tasks on ordering events. I mean, I'm pretty sure there are. I don't know if it's probably with stories. Might also be based on the rock stories, because there are a lot of data sets based on that. And I don't know if there is any benchmark for removing a sentence to make the story reasonable, but it sounds like a very good idea. If there isn't one, then maybe there should be one. So yeah, good idea. Okay. Let me just quickly check something. I'm sorry. Okay. Another question? Oh no, it's just thanks. Okay, so let's move on to the third part, acquiring common sense knowledge. So we're here in symbolic knowledge. And I'm going to start with an example story. It's called Grandma's Glasses. Tom's grandma was reading a new book when she dropped her glasses. She couldn't pick them up, so she called Tom for help. Tom rushed to help her look for them. They heard a loud crack. They realized that Tom broke her glasses by stepping on them. Promptly, his grandma yelled at Tom to go get her a new pair. So that's a fascinating story. And so humans reading this story will understand it based on not just what is written explicitly, but also be able to relate it to their personal experiences and to their world knowledge and common sense. And so we can simulate this part, the world knowledge and common sense, by building common sense resources or knowledge bases that would be kind of like a bank of knowledge for machines to be able to reason about. So let's go back to the story, and now let's see if we use ConceptNet and Atomic, which are knowledge bases that we'll discuss in a few minutes, what kind of knowledge we can extract about this story. So first, we can focus on things that are already mentioned in the story and see how they relate to each other. So for example, ConceptNet tells us that glasses are used for reading, and that if Tom broke someone's glasses, they will want to go get her a new pair. Then we can also take it a step further and make inferences about things that are not necessarily mentioned here. So we're going to start with words that appear in the story and then try to extend it. So for example, we can learn that reading is a type of activity that is a sub-event of relaxing, that glasses are capable of improving one's vision, and that if someone heard a loud crack, then they must feel nervous. And now let's do some kind of an overview of what resources are exist today. So let's start with Psych. This is the Psych project it's from the Word Encyclopedia. It was started by PsyCorp in 1984. And they collect this knowledge from experts and represent it in symbolic logic, as you can see here. So it is very, very expressive. You can express a lot of facts about the world with this complicated logic. It consists of propositional logic, first order logic like quantifiers, second order logic, modal logic, which is like possible worlds or temporal modalities, non-monotonic logic, closed world assumptions, defaults, etc. It's okay if you don't understand half of what I said right now. I just want to say it's very, very expressive. You can have a lot of very nuanced and complex rules about the world. Unfortunately, it is proprietary, but there is an open psych version for research that is available. The problem with collecting knowledge from experts is that it never ends, because as I've been saying, psych has been going on since the 80s. It's almost 40 years that it has been collected. And as of 2017, it contained 24.5 million axioms that had taken well over 1,000 person years of effort to construct. So that's a lot of human effort to construct it. And so there's an alternative approach of, instead of collecting this knowledge from experts, you can crowdsource it, because it's common sense. It's something that we're all supposed to have, right? The only thing you need to change here in order to do the crowdsourcing is that you can no longer use logic or any kind of complicated representation, but then you could use natural language. This is what is done by ConceptNet. It's a very large and very popular common sense knowledge base. We've already seen some examples. Here is, for example, various inferences for the entry for reading. So reading is sub-event of you learn, turning a page, learning. It is the effects of reading might be learning, getting ideas, or getting a headache. It is a type of activity, a good way to learn, etc. Yet another approach to collect this knowledge not from people is to extract it automatically from a text corpus. This is what is done, for example, by NEL, Never Ending Language Learner. It is a project that started at CMU in 2010. So the main idea here is that they started with a seed of knowledge. So for example, they could start with something like Michael Jordan is an athlete, and Serena Williams is an athlete. And then they iteratively find patterns in the text corpus that express this kind of relationships. And then they learn new inference rules and new instances of these rules. So for example, they might learn a new instance like LeBron James is an athlete from the same patterns connecting LeBron James, an athlete, and Michael Jordan, an athlete. And they might also learn inference rules, like if someone, if there's a noun phrase 1 and noun phrase 2 in a plays sport relationship, then noun phrase 1 is an athlete and noun phrase 2 is a sport. And then iteratively learning more inference rules and more instances. And it has been, I think it's still going on. It has been, it started in 2010. There are over 50 million facts in NEL. Of course, it's much larger than other resources because it's automatically constructed. For several reasons I'll discuss later, there are some drawbacks to this approach of extracting knowledge from text. So they did have humans, at least in the beginning, I don't know if they still do, to verify these automatic inferences. And then there's an example in their paper with this really fun error that says that files are baked goods. Anyone has an idea why? Okay, I'll tell you why. So it's because of the following inference. You can delete your internet cookies and you can delete your files. So internet cookies, and if internet cookies are baked good, then files must also be a type of baked goods. Bit of a strange inference, but the confusion here is because of the two senses of the word cookies. There's also WebChild that follows a similar approach to NEL. And finally, Atomic, which is using crowdsourcing and the knowledge is represented in natural language, similar to ConceptNet, but the type of knowledge there is different. It consists of inferential rather than taxonomic knowledge. Let's elaborate on that. These are the statistics. It's actually larger than that. There's a newer version that's much larger, but basically it's about kind of like social situations, and it has knowledge about the causes and effects. Here's an example. X repels Y's attack. X and Y here are placeholders for people. X is the subject of the event and Y is someone else. It could be one or more people. And Atomic distills this type of inferential knowledge into 9 dimensions that you can see here around the event. So first of all, there are causes. So why did X want to do that? And what did X need to do before that? That's a prerequisite. So intent and prerequisite. There are also effects. So what will happen what will X want as a result? What will X feel as a result? What is the effect on X? And then the same for others. It says Y here, but it's typically just others. It could be a person that is mentioned, or it could be also for someone who's not mentioned. Like we're going to see an example soon. Any questions before I talk about building a new resource? Okay, I'll continue. So when we design a new resource, so some things we already discussed, mentioned. So one of them is the representation. So there's this trade-off where you can use symbolic knowledge and be able to express a lot of knowledge about the world. And this is what is done by NEL and Psych. But then if you want to collect it from crowdsourcing workers, then you can't actually ask them to learn logic. So you would have to settle for natural language, which is less expressive. Here's an example from ConceptNet. Oh, sorry. So here's an example from ConceptNet that says a person is located in a restaurant. So that's very ill-defined because it could mean a lot of things. It could mean that all the people are in all the restaurants all the time, or that a specific person is in a specific restaurant sometimes, or you could think about many other interpretations. That's one consideration. The second consideration is what type of knowledge you want to collect. So you could focus on a specific domain, or you could target a broader domain and cover less of it probably. You could have different types of knowledge, like semantic or taxonomic knowledge, like most of the resources, or inferential knowledge, like when you have, like in Atomic, when you have an event and what might or plausibly happens before and after the event. And the third type is the acquisition method, which is a bit related to the first point. So collecting knowledge from people versus collecting it from text. And I want to have another discussion. Anyone wants to mention either advantages or disadvantages of either one of these approaches? I think you can feel free to unmute yourself because most people are shy, so I don't think two people are going to speak at the same time.
Yeah, one thing with collecting knowledge from text is that text usually doesn't contain these kind of common sense scenarios easily. Like common sense is something which we assume when we write an article or when we talk to people. So since we collect data from sources which are meant for people to read, I don't think we explicitly mention a lot of things. So
Yeah.
that is, so we might miss some things if we just use text for collecting the knowledge.
Exactly, that's perfect. Yeah, that's definitely one of the disadvantages of collecting from text. Thanks. Anything else? Something in the chat, let's see. Extraction of knowledge from people is more informative. Text may be subject to reader's bias. That's, it is true and untrue at the same time. It's interesting because I think it also depends on who you ask. I mean, the crowdsourcing workers or the experts might also have their bias. I have a good example for that actually. It's not exactly common sense, but the WordNet lexical resource is very US centric. There's the level of knowledge, level of specificity about different domains is very different. So there is a lot of knowledge about things that it's supposed to be lexical knowledge. It's supposed to be just about the meaning of words, but you do have some kind of like word knowledge about things that are related to the US specifically. And I think there are also some kind of like a lot of there's some domains that were more specific than others because they had more experts on this domain. So I mean, you could have this bias either way, but definitely, yeah, text, yeah, starting from text also has this bias. So thanks for raising this point. And someone suggested to collect from text on social media. That's, yeah, I mean, that's definitely, in general, I would say collecting from diverse texts is a good idea. Yeah, you don't want to collect only from Wikipedia, but also not only from social media. Okay, good. So let me summarize that and add a few points. I think you didn't mention something because it probably seemed too obvious to you. So because we mentioned it earlier, so it is very expensive and takes a long time to collect knowledge from people. It is especially true if you collect using experts. For example, it could take you 40 years and you don't finish collecting all the common sense knowledge in the world. But as I don't know if I didn't show the statistics for all the knowledge bases, but NEL is larger than the human curated knowledge bases because it's faster and it's, well, okay, it's an unfair comparison because it's been running for a long time. But even when you crowdsource, it takes a long time and it costs a lot of money to collect knowledge. And the existing resources, the fact that we're talking about it and we're not just saying, okay, these existing resources exist, let's just use them, is because they still don't cover a lot of types of knowledge because there's just a vast amount of common sense knowledge. And then when we extract from text, and so we talked about NEL, but let's look at the recipe for extracting from text. So basically, you would typically parse the text to extract these triplets, like open information extraction. So you extract these triplets of noun phrase, predicate, noun phrase. Like for example, from this text, you might extract that Brownback is a senator, that Brownback is in Kansas, and that maybe Kansas is a senator. That's the wrong one. And then you want to score these triplets based on frequency. So you exploit the redundancy of correct facts in the corpus. If something is correct, it might be mentioned often. And then you can learn to some threshold above or below which you don't consider the extractions. And as Sahithya mentioned, there's a problem called reporting bias. And the problem is because people only communicate what they think to be interesting or new. We don't tend to talk about trivial facts because everybody knows that. And then as a result, facts that are exceptional are reported disproportionately in text. This problem is known as reporting bias, and there was a paper in 2013 that had this really nice example that everybody has been using since then, where if you look at corpus frequencies, you might learn that people murder more than they breathe because nobody talks about breathing. You just do that without thinking, and murdering is something that is newsworthy. And yeah, but it's fortunately not as common as breathing. And so this is a very serious problem. Related to that, you also don't get any kind of assertions, or you rarely get any kind of assertions talking about what is not true in the world. And this goes back to the frame problem, where you actually do need models actually do need to know everything that is not true for a given situation in many cases. And it's hard to get that from text because we don't often talk about what is not true. Some considerations, this is not about the collection method anymore. This is some considerations when you use knowledge base, common sense knowledge bases. So one, I think I have two of them here. One of them is that many of these knowledge bases work at the word level rather than the sense level. So here's an example from ConceptNet, where if you look at the entry for mouse, then it says that it is located either in a hole in the wall or on your desk, which hopefully only the animal sense is in the, sorry, it refers both to the animal sense and the computer device sense, and hopefully you don't have an animal mouse on your desk. And so when you use it for your model, you actually need to disambiguate and choose the inferences that are relevant for the context. And that's just the very basic example of what not to consider. But I mean, we're going to talk about it actually in the next session. And here's another example, and someone brought it up earlier in the chat. So thanks for mentioning that. That I talked about how common sense is commonly shared among most people, but many of these are actually culture dependent. So here's a nice example that I heard from Robin Spear, who maintains ConceptNet and developed ConceptNet. And so ConceptNet is available in multiple languages. So if you look at the English entry for breakfast, you can learn that it is you can see what are the instances of breakfast. So these are foods that are contained in typical breakfasts. It is very American, I would have to say. It contains like, well, I mean, it's international foods, but most of it is sweet. So you have like churro and brioche and croissant and eggs Benedict, et cetera, et cetera. But then if you look at the Chinese entry for breakfast, and I guess there are people here who can actually read the Chinese, but I used Google Translate to translate it to English. And so it says, for example, that breakfast is made of noodles, which is not something that I would consider as breakfast, for example, but I guess a lot of Chinese people wouldn't consider croissant as a good breakfast. I don't know. So that's interesting. And it's much more of a problem when you work on social common sense, because it really varies by culture But even in something like that you think, well, it's everybody agrees on that. They don't. I think that was the last slide for this session. So let me just look at the chat. Imagine if we learn common sense from Twitter. Yeah, definitely. Yeah, I think, let me stop sharing. There's definitely bias in the corpus that we learn from, so it's something to consider. Okay, any questions before we go on a break?
I have a question.
Yes.
So, yeah, so like we talked about acquiring from text is kind of challenging because of reporting bias, right? So we only talk about new or surprising events, kind of which don't happen normally. So is it possible to retrieve this kind of knowledge by looking for events which have this kind of but, or, you know, like usually something happens, but it didn't, like sentences which are framed this way, and the reverse of that can be considered as common sense?
Yeah, that's a very good question. It was actually suggested by the authors of the reporting bias paper. They talked about something called disconfirmed expectations. So they have this example in the paper where they say something like, what was that example? Like someone, I think Sally, it's like always like very morbid examples, but Sally hit her car or crashed her car into a wall, but she didn't get hurt. So you learn from that if people crash their car into a wall, they typically get hurt. And then they only suggested it as something you like people might want to do. And I actually tried to do that last year with using language models. But I found that language models were not good at that. I mean, okay, they didn't do that because the signal for that is actually quite sparse. So if you look for these kind of sentences in a corpus, you will not find enough sentences for each scenario that you can actually teach. You can actually learn a significant amount of common sense knowledge from that. I tried to do that with language models, and I learned that they're just. I mean, I reconfirmed the same thing that people found, that these models are not very good with negation and like various types of discourse, like but or yet. So unfortunately, I mean, I still think it has a potential, but yeah, it's not trivial to get that type of knowledge.
Yeah, thanks. Yeah.
Let's look at the other questions. Is the old-fashioned NLP still competitor for the new era neural NLP? So I think it depends on how you define it. I think the short answer, the official answer is no, because if you look at the benchmark performance, it's really hard to beat the, training the largest model on the biggest amount of data. You still get the best performance. But if you really care about not just about the performance on the benchmark, but you know that sometimes it's misleading, as I mentioned. So I think there's some work, especially in common sense, more than in other areas of NLP. There's some work on trying to incorporate symbolic knowledge into models. This is what we're going to talk about in the next session. And trying to maybe incorporate older methods or redevelop older methods that didn't work in the past and combine them with neural models. So there's an understanding that it's not good enough to just have neural models, but it's also hard to show that you actually get any performance gains from incorporating any other approaches right now because of the way that our benchmarks are built with all these biases. Question, how metaphors play a role in common sense? Oh, okay, that's a good question. I'm actually not going to talk about it in this tutorial, but I worked on all kinds of figurative language. And so I have a preprint that I can share later, or you can just search it on arXiv, search my name on arXiv, that kind of like connects these two things, where we show that if you want to interpret a metaphor, you often you can do that often by using common sense knowledge. So actually, sorry, we didn't work on metaphors. We worked on similes, but it's similar enough, I think. So we had an example where it was mentioned about someone that they are calm like a mountain lake without wind in it or something like that. And then in order to for us to interpret what it said that they are like a what was that, a mountain lake without a wind. And then in order for us to understand that it means that this person is calm, we need to know something about the properties of a lake. So we did something with that, with incorporating external common sense knowledge to better deal with metaphors, or sorry, with similes and idioms. So I do think there's a lot of connection. There are very few people working on these two, on the intersection of common sense and figurative language. But I think it's, yeah, I think one can inspire the other in these two areas. Okay, I think we can take the break now. So it's going to be half an hour, so we can come back at whatever your time is in half an hour from now. It's going to be 7 p.m. at my time. So see you in 30 minutes. Okay, I think we can continue. So we have two more sessions left, and then the last one is going to be dedicated to questions. But again, feel free to ask questions in the chat during the session. So this session is going to be about methods for common sense reasoning, and we're going to use the and it's going to include both the neural representation part and also the part where we put everything together and we talk about developing methods that use this symbolic knowledge from knowledge bases that we discussed in the previous session. So I'm going to use the Winograd Schema challenge as an example throughout most of this session. So just a reminder, or if someone joined late. So this is a pronoun resolution task where you need common sense to be able to resolve the pronoun. So for example, the city councilman refused the demonstrators a permit because they advocated violence. They advocated violence. They refers to the demonstrators, but if it's changed to they feared violence, then the answer changes to the city councilman. So I want to ask for your ideas on how you would develop a model for Winograd Schema challenge. Any ideas? Okay, we have an idea in the chat. See, transformers. Yeah, that's a good start. That's a good start for any NLP model. Indeed, we're going to talk about some transformer-based models. Attention. Okay, yeah. Can current methods obtain? Current methods to obtain pre-trained vectors work? Yeah. So these are all definitely relevant answers for the neural models. Okay, so maybe let's look at a more complete example of how it would work. So this is the standard supervised approach for basically any kind of multiple choice or with a slight variation classification task, or I should say classification task or with a slight variation multiple choice. The idea here is that you build these statements. Each statement is basically the context or your question. In our case, it's the sentence in the Winograd Schema challenge. And then you assign each one of the answer choices separately into the context. So here, for example, you would replace the pronoun they with each one of the answers. So you have two options. So you have, and then you typically, if you use something like BERT, you would also include the special tokens. So you would have something like CLS, that's the beginning of sentence, special token for bird. The city councilman refused the demonstrator as a permit because, and then you typically would put a separator before the start of the answer. So that would be separator, the city councilman advocated violence. And then the same thing for the other option, which is the demonstrator advocated violence. Then you feed each one of these to BERT. You get a vector, you get vectors for each token in the sentence, but you can, you typically use the CLS, the vector corresponding to the CLS, which somehow summarizes information about the entire sentence. And then this is fed into some classifier. Again, I'm not showing all the details of the architecture here, but this is fed into some classifier that's on top of BERT. And or if it's a classification task, then it's a classifier that predicts the output is the number of labels. And if it's a multiple choice, then you need to score each one of these separately. And then you take all the scores and you normalize them with softmax to get a distribution. So that's like the most standard way to train supervised models for multiple choice tasks these days. It works for WSC, but it works for other tasks as well. And then the equivalent unsupervised approach is also using language models. Here, it's more typical to use standard language models. So I didn't mention that earlier, but in case you don't know, masked language model like BERT is where you can mask. It was trained such that words in the middle of the context or anywhere in the sentence are masked out, and then the model needs to guess them from the surrounding context. While standard language model is trained to predict each word given the beginning of the sentence. And so, or you might know that as causal language models. I don't really like the name because I think it implies that there's some causality happening, but it's just like, it's just the order. I mean, it's a term from electrical engineering, I was told, but I think it's confusing in the context of language models. So we're just going to call them standard language models or left to right language models if we're talking about English, which is left to right. And so the way that this unsupervised approach would work is very similarly. You create this statement or sentence for each one of the answer choices by replacing the pronoun with each one of the answers. And then you compute the language model score of each one of these statements. That would be cross entropy loss or something similar based on the probability of predicting each token in the sentence. And then you predict the answer choice corresponding to the better language model score. This specific paper that I'm citing here, I think it was one of the earlier ones to use language models for that. Probably missed something. Now when I say that, it doesn't make sense that the earlier ones was in 2019, but this is using, this was actually using RNN-based language models, but the technique is similar, so it doesn't really matter, the underlying representation. And something else that worked well for them was that they trained multiple language models on different corpora, and then they ensemble the predictions. So basically, just averaging the predictions and that improved the performance. So why does it work? Why does language model score? Why can language model score tell us about which answer is the correct one? Anyone has an idea? Okay, we have answers in the chat. Okay, context and can be associated to token. Yeah, I think these are short answers, but I think they basically cover the two things that I wanted to say, and they're considered how each word is related to each other word. Yeah, so there are two things that happen here, and I think the line is pretty fine between them. One of them is that, as I mentioned earlier, these language models, because they're pre-trained on a large text corpus, then they learn about the world. So we could use them as a proxy for telling us what is more plausible than something else. That's one. That's like the positive way to look at it. The more negative way might be that there's just statistical patterns, like a sentence that is more, or maybe saying something about the way that the data set was built. Maybe the so I wasn't using that example, but there's a famous example that is almost always used for Winograd Schema challenge. That is the suitcase. The trophy couldn't fit into the suitcase because it was too large or it was too small. And then something like that, you could have some statistical patterns or some. You could have a sentence in the corpus that says something about the suitcase being too small versus nobody saying the trophy is too small. So that, I mean, it's like that's why I said it's a fine line, because you could still say, well, it is word knowledge, so it's valid. But both of these, what I'm saying is that they're learned because of all these statistical patterns in the corpus. So it's basically because the model learned a lot about the world and about what is more plausible than others. I wasn't planning to go into it, but there are some issues with the way that we use language model score for plausibility. I can maybe talk about it in the end if we have time. Okay. So yeah, as I've mentioned, this pre-training step for language models teaches them a lot about the world. So first of all, they learn a lot about syntax, which basically shouldn't really help them in Winograd Schema challenge, because the entire point is that there's a pronoun that could be replaced syntactically with each one of the options, but just like semantically, it makes more sense to replace it with one of them than the other. But it could help sometimes. Semantics, so it could learn, for example, that specific entity types could be more plausibly related to specific actions, like learning that, I don't know, inanimate objects can't eat, or something like that. That could potentially be useful in some examples. And so there's also something called thematic fit about, I mean, it's kind of related to what I said, to learn what are the plausible types of arguments for each verbs. And then you could also say, I mean, it is related eventually to factual knowledge, a lot of it. And these models have pretty impressive knowledge. They know a lot of, they capture a lot of things that most people actually don't know. This is actually not common sense. This is an example from a paper that I actually didn't cite here. I think it's from Language Models as Knowledge Bases. So yeah, it has impressive amounts of knowledge. At the same time, the knowledge in pre-trained language models is not the most reliable thing. So for example, one of the problems that I keep running into, not just with language models, but it used to happen with word embeddings as well, that these models, they're trained in, it's called like a distributional manner. It's based on the distributional hypothesis that the context of a word can tell us a lot about the meaning of the word. And while it is obviously true and very useful for NLP, it also has a problem where these models confuse semantically similar, mutually exclusive terms. I know it's a complicated phrase, so I'm going to give this example. This is an example from a paper by Zhang et al., where they show that if you query BERT with something like DirectX is developed by, then first of all, it is already impressive if BERT has this knowledge, because it's probably not mentioned very frequently in the corpus, maybe once or twice. Or no, maybe it's in the news, but yeah, it's not something that everybody knows. But the problem is that BERT somehow knows that it should be a company name, and maybe even more specifically a software company. but it doesn't necessarily know which company is the correct answer. And so it answers all these companies with very similar scores. And in fact, the second option here is the correct one, Microsoft. And so it could be because BERT doesn't know the answers, but it probably is so because the representation of these different companies is just similar. And it has been shown for other types of knowledge. Like I had a paper where I showed that it does the same thing for colors. So if you ask it what color is a dove, for example, then it tells you red, green, black, all kinds of colors that are not colors of a dove, just because it knows that based on the syntax, it should be color name, but it doesn't necessarily know the answer, and it confuses all the other colors. So that's one problem. And then there's also a related problem that these models are really bad with negation. This is really bad for reasoning because, and also for extracting knowledge, because you can have a sentence like something is not true, and then it would learn that something is true. Or for example, if you use BERT to generate or complete knowledge, then it completes the sentence birds mask fly with both can and can't, with similar probabilities. Even though they have an impressive amount of knowledge, as I've shown in the previous slide, there are some areas where they don't actually have a lot of, they have a lot of missing knowledge. One such area is perceptual knowledge. So this is things that we see or hear, and then we don't need to talk about it because we see it. But these language models, they only learn from text, so they don't learn these kind of things, like physical properties of things, or all kinds of physical common sense is kind of hard to learn from text. And as we talked about in the previous session about extracting knowledge from text, language models also suffer from reporting bias. So differently from text, from extracting directly from text, they do overcome some parts of reporting bias. So many things that are too trivial to appear as is in a text corpus are still somewhat captured by language models because they can, to some extent, read between the lines by aggregating across different contexts. But at the same time, they exaggerate even further the probabilities of very rare events. For example, this is my favorite example. If you use BERT to rate or like compute some kind of probability or of frequency of actions and events that people do or that happen to people, then it really overestimates the frequency of dying, even though it's something that only happens once in a lifetime. And that's because, I guess it's because it's primarily trained on Wikipedia. And in Wikipedia, you have all these bios of people from history that are, influential people from history that are often already dead. And this is not just limited to BERT. If you use GPT-2, I guess GPT-3 as well, if you use it to generate a story, it very often deteriorates into someone and ending up in a hospital or dying. Very morbid stories. Okay, let's look at the questions in the chat quickly before I move on. Okay, are there available tools to extract parse trees from representations? I'm not sure. I know the group at NYU has been working on extracting or like learning latent trees in representations. I don't know if they have anything about extracting it, but I would look there. I would probably look at the works by Sam Bowman and his group. They might have something for that. Can we combine knowledge base with language models? Yeah, excellent question. We're going to talk exactly about that. So thanks for asking that. And yeah, and we already have an answer for this question that I didn't even read yet. So thanks. Okay, so this is an example from Winograd. It is the large-scale version of the WSC dataset. It is much larger. It's like tens of thousands of examples. I don't remember exactly how much. And it is more difficult. It is adversarially filtered. And another difference is that they don't have a pronoun, but they have a placeholder. But other than that, it's the same. So here, Katrina had the financial means to afford a new car, while Monica did not, since one of them had a high-paying job. And as the answer in the chat already says, the answer here is Katrina, is the one that had a high-paying job. If we just use BERT off the shelf without training it to try to solve this question, we can just replace the placeholder with a mask. This is a BERT demo from Alan NLP. And then, well, it is not constrained only to the two options, which are Katrina and Monica. It could predict any token from the vocabulary. So I don't know why, for some reason, it predicts new line with a very high frequency, a high probability. But the second prediction is fine. The word she, it is correct, basically. It's just not very informative because we're trying to figure out who is she. And then among the two names, the only one that is predicted in the top 5 predictions is Monica, and this is incorrect. Yet, if you look at the performance of, well, BERT has like a decent performance on this data set. Roberta has a better performance because it's trained. You have to train it. But we could also look at knowledge bases and see what kind of knowledge can help us in this context. So I took some of the words in the context and I tried to search for knowledge-based paths between them. So for example, we can learn that job is used for making money. Spending money requires making money. Buying requires spending money. A car is something you can buy and it is capable of costing a lot of money. This is from ConceptNet. And I would actually like to have more knowledge here. So let's say we found additional edges in ConceptNet. So for example, that a high-paying job is a type of a job, specifically one that gets you, that makes you make a lot of money. That arguably, to spend a lot of money, you need to make a lot of money. That to buy something that costs a lot of money requires spending a lot of money. That car is something that is, something that you can buy that costs a lot of money. And maybe you also want to delete this edge so that you can only buy a car if you have a lot of money. So let's assume we had all this knowledge in some knowledge base, and then this would be the main or the general approach, neurosymbolic approach, where we use this symbolic knowledge from a knowledge base, some kind of a subgraph maybe that we extracted from a knowledge base related to some concepts and entities and events that are mentioned in the context. And then we also have some vector representation of the context or the answers or both. And both of these are going to some model that somehow combines them together. So there's like a general recipe for neurosymbolic models for incorporating external knowledge into neural models. I mean, it's a recipe with different variations, and it calls for 3 ingredients. The first is the knowledge source, where you're going to get this symbolic knowledge. The second is the neural component. And the third is how you combine them. So the first one, the knowledge source, is this is a slide from about 1.5 years ago, where most of the models, almost all of them, were just using ConceptNet. But Atomic and Comet, that we will discuss soon, became more popular since. So I think most of the, later on, many papers use Atomic, and now most papers use Comet. But I mean, there are many other ways. They're just less commonly used. You could use lexical resources like WordNet. You could mine inferences directly from a corpus, or use other knowledge bases that we mentioned in the previous session. You could define constraints or handcrafted rules, and you can use all kinds of tools like special embeddings, or that were trained on knowledge bases, or tools like sentiment analysis or coreference resolution, etc. The neural component, I think, is the least interesting part, for me at least, because I think typically we just use the newest and shiniest model. And then the combination method is the most interesting, I think. So there are many ways to combine the symbolic knowledge with a neural model. I'm going to mention 3 of them, and we're going to see examples for 2 of them. So you could do some kind of a multitask learning. You could embed the symbolic knowledge into some kind of vector representation. And someone mentioned earlier attention. So yes, this is where attention will be useful. And you could also somehow modify the scoring function that defines how plausible each answer choice is. Let's talk about the first 2 methods. So the first example is for multitask learning. So this is a model that was developed for rock stories, I think. So we mentioned that earlier. That's the 5-sentence story that you need to determine which of the 2 sentences are the more plausible continuation. But it is a multiple choice task, so you could do exactly the same for WSC or any other of the tasks that we discussed earlier. The neural component here is just a standard multiple choice BERT model. So again, you create a statement from each combination of the context or the question with an answer choice. Then you have all this, in this case, you have 2 endings, 2 possible endings. So you have 2 statements. You encode each one of them with BERT. You feed it into the scorer. You get a score for each answer, and then you normalize the probability using softmax. So that's pretty standard. How do we get any kind of common sense knowledge into BERT here? So they used a pretty elegant and pretty simple method, which is multitask learning. So they have 2 auxiliary tasks that they train BERT on. So and it is supervised by ConceptNet. So for pairs of words that appeared in the training set of the main task, the rock stories data set, they train the model to predict first if they are related in ConceptNet or not. So for example, restaurant and food are related. And second, what is the specific relationship that holds between them in ConceptNet? So for example, here it's going to be restaurant serves food. And this is the first one is a binary classification task, yes or no. The second is a multiple, it's like a multi-class classification task, so over all the different relationships in ConceptNet. And the way that it works is that when BERT is trained on these tasks, the loss from predicting the answers to these questions is back propagated into BERT and updates BERT, and then this knowledge is kind of instilled into BERT. And that's useful for the main task that uses this BERT instilled with knowledge from ConceptNet. So that's the more general maybe way, the generic way that you can incorporate knowledge into BERT, and it's also like a softer way to incorporate the knowledge. You don't need to know anything about the task, but you also can't tell if this knowledge is going to be eventually used by the main model or not. The second approach is to embed the symbolic knowledge into a vector. So this example is for a task called Commonsense QA that I think I didn't mention. So this task is it just asks general common sense questions. And for example, you have something like, where would I not want a fox? And the answer is at a hen house. And we can understand because of our common sense knowledge why it's not a good idea to have a fox there. And the other answers, they don't seem really related here, but they are related. Like I think probably there are foxes in the mountains and in England and California. So it should be, it's supposed to be a little bit confusing for the models. So here the neural model is again using BERT, but it's not fully trained as a separate component. It's just used to provide a vector representation for the statement. The statement here is again the question followed by a candidate answer. So here, for example, we have the question, where do adults use glue sticks? And one of the answers, this is specifically the correct answer, office. And then you combine these two together, you create these statements with BERT's special tokens, and you fit it into BERT, and you get a vector representing the sentence. Typically, you would take the token corresponding to the CLS vector. But then it is not it's not directly fed into the model. It's not fine-tuned yet. It is further combined with knowledge from a language model. Sorry, from knowledge base. They're also using ConceptNet, and specifically, they first retrieve a subgraph relevant to the concepts that are mentioned in the context and the question. So for example, here you can tell that adults are capable of using glue stick at location office, which is perfect. It's really useful for this question. And then they also have some kind of a pruning mechanism to keep a smaller subgraph, because you could extract a lot of knowledge from ConceptNet, but much of it is not relevant. And then they embed this knowledge with an LSTM path encoder, while also using attention mechanism to attend to the words in the context. And the result of this is graph vector, which is then combined or concatenated with the statement vector and fed into an MLP. So now the classifier can learn for each instance how much of the symbolic knowledge to use and how much of the neural representation to use. So this is also it's also a way to a pretty generic way that you can use for many different tasks, it's, I think, more it's a more straightforward way to tell if the model is actually using the knowledge, the symbolic knowledge, or not. Okay, I'm gonna keep that back for a few slides later on that I'm gonna mention something. Yeah, okay, it's actually the next slide. Any questions so far? Okay, hopefully there are no questions because it's clear, not because you lost me completely. Okay, so let's talk a little bit about the limitations of these kind of neurosymbolic methods that we talked about in general, not just the two examples that we saw. So first of all, we mentioned in the previous session that knowledge bases unfortunately have limited coverage because there's just a vast amount of common sense knowledge, and it's almost impossible to represent everything with a knowledge base. The second problem is that these kind of inferences or knowledge that is encoded in these knowledge graphs sometimes is only relevant in certain contexts. And we saw the example earlier with the mouse in ConceptNet, which has knowledge both about mouse as an animal and about mouse as a computer device. And then if your model wants to make some inferences about, I don't know, where do people use a mouse, and then one of the options is office, then you want only to get the inferences that are related to mouse as a computer device, like that it is located at your desk, on your desk, and not that it is in a hole in the wall. And so that's one element, but of course, I mean, this is just like the most straightforward example of that, but some things, I don't think I have an example for that here, but in Atomic, for example, you have all these kind of inferences that are plausible. They're not necessarily true in every context. I think we're going to see an example for that soon. Another problem is that there's this trade-off between coverage and precision. There always is. So when you use knowledge from knowledge bases, you need to decide on what's the longest path that you would consider. And then the longer the path is, the less precise it is, because basically, I think there's even a game, I don't know the name of the game in English, but a game where you just take two completely random concepts and you find some like chain of concepts that are related to each one of them, and then you end up being able to connect every two random concepts. So yeah, that happens in knowledge bases as well. This is an example of a pretty short path, actually, just 3 or like 2 edges, where you can connect kitchen to kill through a knife. So yeah, you do lose precision from indirect relationships. There's also a trade-off that we sort of discussed with the example that we saw, where how do you use the knowledge in a neural model? So if you embed it, then you get better generalization, and it's also mostly task agnostic. I think you can typically just use same kind of approach for many different tasks without knowing something about the task. While if you want to make sure that the model uses it, and if you can define it maybe as some kind of like hard constraints, but then it's more task specific. You need to know something about the task. It's harder to do that. It's less possible to generalize like that. It has to be like sometimes like exactly as it is written in the knowledge base. But it's probably more accurate than embedding that knowledge, because if you embed that knowledge, you can get the problem that I mentioned earlier, where a language model just confuses mutually exclusive terms. So that's a trade-off. Let's look, we're going to see a kind of a solution to the first 2 problems. I just want to make sure there are no questions so far. Okay. So let's move on. So the solution to the first 2 problems, or maybe I'll just repeat the first 2 problems again. So the problems of limited coverage by the knowledge bases, and the fact that the knowledge base is out of context, and you have to find and connect the inference, find the inferences, specific inferences that are correct in your context, or relevant in the context. So Comet is a knowledge model that is, it's basically a language model. Specifically, originally it was using GPT. The latest model is using BART, I think. And it is trained on a knowledge base. So this is pretty similar if you know knowledge-based completion methods. It is the same idea. It's kind of different because it is a generative model. So here, for example, this is an example of how Comet was trained on atomic. So you have the left-hand side event, like person sails across oceans. That's called head entity here. And then you have the specific relationship that you want the model to predict. So for example, requires. And then you train the model to predict the event in the right-hand side event in atomic. So for example, before the person sails across oceans, that person needed to buy a boat. And then this is trained as with a regular language model objective. So basically predicting those words, and then the objective is a negative log likelihood or cross entropy loss. And what you get eventually is that you have from the language model you trained, so you have a language model that you trained to predict structured knowledge. So it is conditioned on a specific type of knowledge, specific dimension of that knowledge or relationship in the knowledge base. And so this is the knowledge part of the model, whereas, sorry, let me rephrase. So it is on the one hand structured like knowledge bases, but on the other hand, it is capable of generating inferences for dynamic situations as language models. So here are a few examples. This is an example from Comet trained on the atomic knowledge base. And the example here is that it's for an event that actually exists in atomic. So, but what I want to show you that is that Comet can predict additional inferences. So for example, if person X gives a tutorial in atomic, it said that person X is perceived as smart, person X needed to be a teacher for that, and others will want to thank person X. This is what atomic had, and there's another dimension of what will happen to others or to person Y as a result, but atomic didn't have any inference for that. And so if you feed it into Comet, it can predict that others will then gain knowledge, which is nice. It is correct, hopefully. And it is capable of predicting knowledge that didn't exist in atomic. Here's another example of what I want to show you here is that it's actually capable of generating inferences even for new inputs. So this is an example from Comet trained on ConceptNet. And ConceptNet doesn't have an entry for listen to tutorial, but if we fit it into Comet, then it tells us that it is located in a classroom. It is motivated by you being smart. It starts with sitting down. It has the prerequisite of listening carefully, and it causes good grade. I'm not going to grade anyone, so don't worry. I'm also not in a classroom, but yeah, most of it is relevant. So why does this work? So what happens here is this kind of transfer learning from language. And so here's an example. If you take Comet trained on ConceptNet and you ask it what mango is, it tells you that mango is a fruit. But if you actually look at ConceptNet, then there is no entry there is no edge saying that mango is a fruit. The only relationship is that mango is used for salsa. And it's not straightforward to infer that mango is a fruit because usually I think vegetables and spices are used for salsa. If you take the same model, if you trained a Comet model on a transformer that is not initialized with not pre-trained as a language model, as a pre-trained language, not pre-trained, like the same architecture as GPT, but not trained on a corpus, then it predicts that mango is a spice, which is more in line with the salsa knowledge. Any idea what is happening here? Okay, I think I may have asked too trivial question. I think the main thing that comes to your mind when I ask something that is probably, well, probably the language model already knew that mango is a fruit, right? So what do we need to train it on ConceptNet for? So yeah, that's a question I'm going to address. So let's see what language models know about this. This is again the demo. This is for next token, so it's using GPT-2. And if you just ask it, you tell it mango is a, then it can put the next word out of the entire vocabulary. So it doesn't really know what you're asking for. So it gives high probability to very generic terms that come after is as something like great, very, new, good, and small. So that's not helpful. Let's see what happens if we change the phrasing. A mango is a. This is getting better. Now we have delicious and sweet that are already related to fruit. And then if we use a capital letter, a mango is a, then now we get that it is a fruit. So two things happen here. One of them is that these models, and it has been shown by many different papers, they're very sensitive to the prompt phrasing. So we basically had the same meaning in all of these three prompts, but the answers, the predictions are completely different. So that's something you need to know about language models. And specifically, another thing that happens here is that as opposed to Comet, the language model doesn't know what type of relationship we're interested at. We're just asking about, I mean, it doesn't know, it doesn't treat the tokens as a structured relationship. It's just another token. So it predicts other possibly correct properties of Mango. So what we get by training on a knowledge base is that we take these language models that implicitly represent knowledge about the world, and we train it on a seed of knowledge, like a relatively small number of examples from a knowledge base, like, I don't know, a few thousand examples. And then what it mostly learns, it learns the structure of knowledge and some knowledge as well, but mostly the structure of knowledge. It learns something about the relationships in the graph, and then you have a model that can then be applied to new concepts and new situations and generalize the structure to new concepts. There's an extension, an extension of Atomic, recent one from last year that has much more relationships and also more examples, more edges in the knowledge graph. It has both the types of relationships from Atomic, the original Atomic, and also more physical common sense from ConceptNet. And there's a corresponding new version of Comet trained on both of them. So if you want to use Comet or Atomic for your work, then I recommend that you use the newer version. It's better. It's also using BART instead of GPT. Okay, that's it for this session. Any questions before we move on to the next session? We're slightly ahead of time, so we have plenty of time for questions. Oh, I think there is a question. Yeah, there's a question in the chat. Okay. How does Comet evaluate these generated inferences? For example, when I feed vegetarian to Comet, it seems to predict both eats vegetables and eats meat in the top 5 predictions, which is not ideal. Yeah, that's a very good example. I guess this is probably because of that problem with, well, I don't know. It might be a problem with, no, I guess that's a problem with negation, right? Probably learned from the corpus that a vegetarian doesn't eat meat, but it's not negation. I don't remember exactly how they evaluated the latest version, but I think in the original one they had human evaluation. I suppose they had in the second version as well. I mean, it's a generative task, so if I remember correctly, they used, I remember they used both automatic evaluation metric, like I think it was blue, but against like the using the knowledge from Atomic, feeding it into Comet and seeing that Comet predicts the inferences that are already in Atomic. But they also had a human evaluation to judge the correctness of inferences that are just not in Atomic. And I think if I remember correctly, they tested both the correctness, but also the kind of like diversity, like how many inferences Comet predicts that are not in Atomic. It might be confusing with another paper, but I think that's what they did. I think typically that's what you would do when you train a generative model. You do human evaluation, because automatic evaluation, I mean, I think we still report that in papers because we people expect to see some kind of an automatic evaluation metric, but maybe even that is changing. I think sometimes reviewers for these papers, they just say, why are you reporting these metrics? They don't mean anything. They don't correlate to human judgments. So yeah, probably, I mean, they did human performance, yeah.
Yeah, I was wondering about this because I was trying to use Comet for a downstream task, and like adding this kind of, some of these inferences can actually be harmful to the task. Like, for example, saying that the vegetarian also eats meat. It's like, we're probably going to make the task worse. That's why I was wondering about the
Right.
evaluation.
Yeah, I mean, I think Comet is one of the more successful examples. It's usually pretty accurate. I actually didn't use the latest version enough to know. I did use it in one task, but I mostly used the previous version, and I was typically surprised by how good it is for a model. But yeah, it's still a model, and it still makes mistakes. It generalizes inappropriately, like saying that a vegetarian eats meat. And then definitely, if you use that, you can harm the performance instead of like helping it. Yeah. Okay, let's see what else. This is me just being lazy, but there is a Python package for Python. Oh, is there a Python package? You mean for Comet? Yeah. Yeah, there is a Python package for Comet. Yeah. So I don't think I don't know if I put a link in the slides. There's a demo, but yeah, someone linked to the demo. Yeah, so there's the demo, but but they have the code available, and you can just I don't know. Yeah, I mean, we've used it. I've used it with a student. You could use their code. I think probably from the demo, there's a link to that. Yeah. Anyway, yeah, there is a Python package for that.
Hi, Prof. Can I ask a more abstract question about common sense?
Sure.
Yeah, it seems to me that's quite intuitive that common sense is a little bit conflated and related to morality, right? So are there different kind of common sense, right? So just now you mentioned physical common sense, and then there's the pronoun thing. And then I think one of the subset could be morality, right? Because given the example just now of Tom helping his grandma, I mean, Tom must be a good person to reasonably predict that he wants to help his grandma, right? So yeah, is there a breakdown of common sense, the different subsets of common sense, and are they studied differently?
Yeah, definitely. That's an excellent question. Yeah, I didn't elaborate on too much like on different types of common sense, but that's a great question. So I think most of the I think the three main types of common sense knowledge that people are working on currently are mostly social common sense, which is related to, for example, the story with Tom and his grandma about like social norms and what is expected in different social situations. There is work on physical common sense, and there is some work on temporal common sense. I think less than the others, but there is also work on that. And yes, some of these are much less common and much more culture specific, or even like they have individual differences. Social common sense is the one that has more, I mean, it varies more between different cultures and people. I think most of the work that is being done right now is coming from groups in North America and focuses on people from North America. I mean, everybody acknowledges that it's not really universal, but it's also hard to work on culturally aware, culturally specific common sense knowledge, because it's already hard to work on universal common sense knowledge. So it complicates things further. And then like most of the work that came from groups in North America, like for example, I mean, I was also involved in some work on social common sense, and even though I'm not from North America, I was in a group it was at AI2, and we worked on social common sense and specifically social norms, and then we collected annotations from workers in the US, crowdsourcing workers in the US. So we did acknowledge in the paper that it's very US centric, but we didn't take the next step to collect knowledge from other countries. I think the people who the first author of that paper, I think, continued to work on that to do something culturally aware, but I wasn't involved in that. You also mentioned something about morality, and so there's like a lot of relationship between social common sense, which is like what is socially acceptable, what you how do we behave, what do we expect that people would feel about things that happen. This is also related to something called naive psychology, that we kind of know we kind of know to predict what others feel in different situations, because we're all similar in some way. So we know what we would feel, so we can predict what others would feel. And so that's like one side of it, but the other side is more like about what is moral, what is correct, what is the good way to behave versus another. It actually had a I mean, I don't know how probably some of you at least heard about the model, the Delphi model from AI2 that tried to like predict what is ethical and what is not, and got them into some trouble because it's still a model and makes a lot of stupid mistakes. And even though they acknowledge that it shouldn't be used for advice, it still raised a lot of criticism. So yeah, I mean, this is something that is kind of complicated, but still people work on that because I mean, like social common sense in general, still people work on that because the models that we eventually, the NLP applications that we want to develop, they kind of need to know how humans feel and what are typical intents or reactions by people for different situations. So it is important to work on that. But I hope that there will be some more work on culture specific common sense. It's just really hard, but yeah, we need to do that.
Thank you. Okay, can you point me to some resources on the social and moral common sense stuff?
Yeah,
like
definitely. Yeah, I'll take a note to do it later. Or maybe you remind me later if I don't remember to do that.
Thank you so much.
Sure.
Can I also ask another question about training? So I think it's quite intuitive that we test common sense using language, but could it be that we need other modalities to train common sense? Or yeah, is there any advantage or work in this space?
Definitely. Yeah, I'm actually surprised I didn't put it in my slides. Maybe I have it in my next session, but I think I don't. I typically mention that that definitely like one of the problems that I mentioned about reporting bias is because of how we learn from because language models learn from text, or the knowledge bases that I mentioned that learn from text, and some things are just not mentioned in text, but they are visible in images, for example, or in videos. And in another slide deck that I'm not using, I have an example where, for example, if a model goes over a lot of images, then it might learn something like that in a class photo, if the kids in the front row are, in the last row are sitting, then the kids in the front row are also sitting. Otherwise, they're going to be blocking the view. And this is something that you would never find in text. Nobody actually talks about something that's so trivial, but you might learn that from images, or something more basic than that, like learning what color a banana is typically. If you search a text corpus, then because of reporting bias, you might learn that bananas are typically green or typically brown, because if a banana is yellow, then it's never actually mentioned because that's the default. So you have like less, the frequency of yellow banana would be lower. But then if you look at images, and assuming that they represent the world a little bit better in that aspect, then you would find that most bananas are actually yellow. So yeah, definitely there are complementary, these two information sources are complementary. one thing that's a bit difficult is that it's not really clear how to extract this knowledge from different modalities. But I think, I mean, some people are already working on that, and I hope to work on that too at some point. Another point to remember is that you could always have different types of reporting biases from different modalities. So, for example, one example that I like to use is that if you learn from videos, and assuming you don't have any copyright issues, you can just train on all the movies ever filmed, then your model will probably learn that people typically hang up the phone without saying goodbye, because that's what people do in the movies. But nobody does that in real life when you're not, angry with someone. So yeah, I mean, we gotta be aware of reporting bias. So I think one way forward is definitely to learn from additional modalities, but also I think even when learning from a single modality like text, we need to develop methods that more like embrace reporting bias and try to work around it rather than just saying, okay, I'm just going to ignore that and learn from the text or from the model.
Okay, thank you. Also earlier in the school, right, we learned about causality and interventions and stuff. So are causal structure models or causal graphs used in solving common sense reasoning?
I don't know of any work that does that. I think there's very little work that I know of. Oh, causality, unfortunately. I know of a few people that work in that. I'm assuming one of them that I think of was probably the instructor of that course. Was it Zach Lipton?
No, not very sure.
Oh, okay. Yeah, unfortunately, there's not a lot of work in causality in NLP yet, but I think more and more people are interested in working on that. So hopefully it would be a part of NLP, a more substantial part soon.
Okay, thank you so much.
Thanks. Okay, let's move on to the last part. So this part is going to be, I think, pretty short, and then we're going to have more time for questions. So okay, so this part is going to be about reasoning and the conclusions and time for questions. So let's talk about different types of reasoning, and then using the Wikipedia definition. So one of the types of reasoning is deductive reasoning, where this is the process of where you get some one or more statements or premises that are known to be true, and then you reach a logical conclusion or a hypothesis from these statements. Another type of reasoning is inductive reasoning, where you have a body of observations, and then you try to come up with a general principle that you can apply to new observations. This is what most machine learning models do, if you think about it, right? It's you get the training set, which is like the body of observations. You have like the situations and their labels, and then you try to come up with a model that is the general principle, and then apply that to new situations in the test set. Both of these types of reasoning are monotonic. That means that when you make a conclusion, it stays true. You can't add, there's no new information that you can add that would retract or make you retract the conclusion or change the conclusion. And although these two parts are by no means solved, or there's not even a lot of work explicitly doing this kind of reasoning. I mean, not by like explicitly trying to work on reasoning. We're actually going to focus on a third type of reasoning, which is non-monotonic reasoning, where you can make tentative conclusions based on incomplete information, Maybe first let me read the definition. Non-monotonic logics are devised to capture and represent defeasible inferences. That is kind of inference in which reasoners draw tentative conclusions, enabling reasoners to retract their conclusions based on further evidence. So yeah, you might have incomplete information. You make some tentative conclusions based on what is more plausible, and then when you get additional information, you can change your conclusion. So this is far less common in NLP, especially in the last few years. I mean, it used to be more common in classical AI. And so, but I'm actually going to focus on this part, the non-monotonic reasoning part, because I worked on some papers related to that, and I think it's an interesting common sense problem. So non-monotonic reasoning is a core human reasoning ability. So that includes, for example, defeasible reasoning, which is the ability to update prior conclusions given additional information. Abductive reasoning, which is reasoning about the most plausible explanation of given observations that might be incomplete. And counterfactual reasoning, which is reasoning about changing outcomes given a change in condition. And I'm assuming if you had a course about causality, which some of you attended, then you probably talked about counterfactual reasoning. So counterfactual reasoning is basically like answering what if questions. Let's talk about each one of these separately. So starting with defeasible reasoning. And I'm going to use the famous example from the 80s that was used in all those defeasible inference papers. So you have the premise that Tweety is a bird, and then it might entail that Tweety flies, or it likely entails that Tweety flies, the hypothesis that Tweety flies, unless you get additional information, for example, that Tweety is a penguin. So you here is used for update sentence. And like other modes of non-monotonic reasoning, defeasible reasoning has been studied a lot in classical AI. But despite the focus of the NLP community on natural language inference in the last, I don't know, 5-6 years, there was almost no work on, or there was no work in the last few years on defeasible natural language inference. And this is actually a very useful reasoning mode for NLP applications. And I'm going to use an example of a summarization system. Let's imagine that you're now training a model to summarize an unfolding news event. Like, I think, sorry if it's triggering anyone, but the most intuitive example I could think of is in the beginning of the pandemic, when you had all these news websites that had these articles you could access even without subscription, that were just continuously updating about the new information that we gain about the virus. So in the beginning, it was only known that, or at some point it was known that the virus is transmitted by animals to people. And then later on, it was also learned that, or discovered that people can also transmit the virus to each other. And then maybe there were other reports that supported it even further. And so any summary that was previously saying that the virus can only be transmitted from animals needed to be updated to retract this conclusion and maybe put another conclusion in. And so in general, any kind of news story that is unfolding and a summary evolving over time should discard previous conclusions and update it. And this is basically defeasible inference. So to work on that in natural language processing, or in general, defeasible inference in natural language, we first of all extended the task. So originally, the task was that the update sentence can only weaken the hypothesis, as in the Tweety is a penguin example, says that Tweety cannot fly. But we also extended it to support update sentences that can strengthen the hypothesis. So for example, if we were told that Tweety is on a tree, that would actually increase our belief that Tweety can fly. Otherwise, how would Tweety get to the tree? So to work on this task, we started with collecting data sets. So we started with existing data sets from various types, and then we augmented them with update sentences that we collected from crowdsourcing workers. So here's an example. This is from the SNLI dataset. I mentioned it earlier. It's the Stanford Natural Language Inference dataset. So for example, there's a premise, a group of people sitting around a table with laptops, and the hypothesis that they might have a work meeting. And we specifically focused on premise hypothesis pairs that were labeled as neutral, because then the hypothesis might be true and it might not be true. So there's room for both strengthening it and weakening it. So for example, the strengthener that we collected was that they're in a conference room, strengthening the fact that the hypothesis that they have a work meeting, and a weakener that they're in a library, because typically people, you should be quiet in a library, but work meetings involve talking. The other data set that we used was, it's basically based on atomic. So we have the left-hand side event from atomic, and then natural language expressing the relationship and the right-hand side. So for example, person X has a pool party, might entail that that's because person X wanted to hang out with friends. To strengthen it, you can say that it was their birthday. And to weaken it, you might say that they actually have a family reunion, so they're not meeting with friends. And the last type of data set that we use is the social norms. And unfortunately, this is the paper that I mentioned earlier about the social norms, and I failed to cite it for some reason, but I can link to it later. So here, there's no premise. The hypothesis is just a social norm that could be relevant or applicable in some situations. So for example, like it is rude to comment on someone's weight. And then the update sentence, the strengthener could say something like, well, especially if they're sensitive to it, you don't want to comment on the weight. And the weakener could be that, well, it is okay to comment on someone's weight if you are their nutritionist. So based on these data sets that we collected, we defined two tasks. One of them is the discriminative task, where the goal is given the premise and the hypothesis and an update sentence to predict whether it is a strengthener or a weakener. And so, as you can guess, we got pretty good performance here, not because the task is necessarily easy, but just because it's a binary classification task. So the baseline is already at 50%. And also because we collected the update sentences from people. And so we had all these kind of annotation artifacts, and the models basically learned to game this task. So that's the less interesting part. We were pretty, it was pretty obvious for us when we worked on it that that's going to happen. We got performance with Roberta that was pretty close to human performance. The more challenging task is the generative task. So here we're just basically reversing the inputs and outputs. So the inputs are the premise and hypothesis, and the type of update that we want the model to generate, strengthener or weakener, and the update, the output is a weakener or strengthener. And this was a much more challenging task. Here, the best model achieved around 60% accuracy, where the humans achieved more than 80%. We also looked at the generations from this model, and so because it's a generative model, and we did human evaluation, but we also manually wanted to categorize the errors. So first of all, a large portion of the predictions were correct. So here's an example. I like this example. This is from SNLI. A man is roaming the streets at night might entail that the man is roaming the streets at night drunk. And a strengthener would be that the man has a beer in his hand, which is pretty cool. Among the errors, so we had a lot of errors that were update sentences that were basically neutral. They were not strengthening nor weakening the hypothesis. So here's an example. This is an example based on atomic. So person X pays their own debt. That might be because person X wanted to be debt-free. And then the weakener that was generated is that person X is in debt to the IRS. Now, I don't know. I don't know if it, I would say if anything, it might be strengthening it because it sounds really scary to be in debt to the IRS. So you might just want to get it over with as soon as possible. I don't think it's weakening anyway, but I considered it as neutral because it doesn't change the fact that person X wanted to be debt-free for better or worse. We also had a lot of cases in which the model was asked to predict a weakener but predicted a strengthener. Again, I think it goes back to the fact that these models, they have a lot of like this very fuzzy knowledge, mixing up semantically similar concepts and ignoring negation. So it's probably related to that. And we had some cases where the models were basically just restating the premise or the hypothesis, which is incorrect. For weakeners, we sometimes had a case where the model predicted an update sentence that was actually contradicting the premise. So the premise is taken to be true. It has to stay true. You can't contradict it. Here's an example. This is based on atomic. Person X picks person Y up the airport. That might be because that before person X needed to go to get ready. And then the update sentence that was generated here is that person X is driving person Y to the airport. But that's contradicting because we know they're driving to get person Y from the airport. And yeah, we had a lot of other errors. Well, not a lot, a few other errors. I see a question in the chat from a while back. Let's see what the question is. Oh, sorry. Okay, it's a direct message. Okay. So any questions on diffeasible reasoning before moving on? I'll wait for a few more seconds because, okay, there's a question. How about falsifiability? Can you be more specific? Can NLP agents reason about scientific statements? Yes, I mean, to some extent, there are some papers on scientific reasoning. There is a lot of work from the Aristo team at AI2. Maybe let me write it in the chat, just they have a lot of work on solving science questions. So they have some work on, for example, tracking stage changes in scientific texts. I think that answers your, yeah, I think that's basically what you meant. Has this kind of diffeasible reasoning used to mitigate stereotypes? I don't think anyone used it for that. I think that's a good usage. It's a good idea. Yeah. So yeah, interesting. Yeah, that's interesting. I guess yeah, I can't think of any work that does that. Okay. So let's move on to abductive reasoning. So abductive reasoning, we actually saw this example earlier, just for the sake of talking about generative tasks. So in abductive reasoning, the goal is to come up with the most plausible explanation of what happened between two observations. So in this example, we saw that between the past observation that Sarah wanted to make dinner for some guests and the future observation that she had to order pizza for her friends instead, we can reason about what happened in between and maybe come up with an explanation that, for example, she realized she doesn't actually know how to cook. This is also very important for NLP. Again, I'm going back to the same argument, the same claim that we really rarely say everything explicitly, because let's say that I was telling you a story. If I mentioned every fact explicitly, it would become a very boring and long story. So I have to assume that you have some knowledge and tell you less than everything, and then you would be able to read between the lines and fill in the gaps of what I'm not saying explicitly. Here's an example. This is a news story from earlier this year. Tesla officially moved its headquarters from Palo Alto, California to Austin, Texas. CEO Elon Musk announced at the company's 2021 annual shareholder meeting. In April 2020, on a Tesla earnings call, Musk lashed out at California government officials, calling their temporary COVID-related health orders fascist and expletive-laced rant. In 2020, Musk personally relocated to the Austin area from Los Angeles, where he had lived for 2 decades. So this is a story that's understandable by everyone, I think, reading it. But there are actually a lot of details that are not mentioned. Like, for example, between these two first bullets, you could more specifically mention that the health orders in California delayed Tesla's production and hurt the profits. So Musk decided to move the headquarters to a state with less restrictions. And this can go on and on and on, depending on how much knowledge you assume that the reader has. So definitely it could be helpful for story understanding tasks. Going back to the task that we actually worked on, this is the art dataset. And it is based on rock stories, so it's using fiction, very simple stories, and specifically, it's just, I think the way, if I remember correctly, the way that they collected it was basically taking the first and last sentence of the 5-sentence story and then just collecting annotations from people about what might plausibly explain these two, what might have plausibly happened between these two sentences. So obviously, we can always train a language model to solve this task, and it has been done. And I think, if I remember correctly, it performs pretty well. But then it would be domain specific. If we wanted to apply it, for example, to the example from the previous slide in the news domain, it's not going to work at all. And so another way to do that is to develop an unsupervised model. And so you want to, the task is basically, if I didn't mention that, the task is to take the past observation and the future observation and to predict, generate a plausible hypothesis. So we have an unsupervised model that I'm actually not going to talk about, but happy to maybe mention it a little later. That we, I'm just going to mention that one of the issues with a language model-based model for such a task is that language models are trained to condition on the past context, but they don't have any objective that trains them to consider the future. So if you just let GPT-2 generate the sentence after the past observation, it's just going to say something like, let's see if I remember that. It was something about she was trying to cook rice noodles or something. And then it doesn't make sense with respect to the future observation. So we had a model that was overcoming that by defining this future constraint and then using backpropagation to update the generated hypothesis. But I guess it's not really understandable when I just explain it like this without the slide. So if we have time later, I'm happy to show that. Any questions about counterfactual, about abductive reasoning before we move on to counterfactual reasoning? Okay, I'm gonna move on. So this is the last type of reasoning I want to discuss, and So in counterfactual reasoning, the goal is to reason about changes in outcomes given a change in conditions, or more simply, answering what if questions. And this is also very useful for NLP applications. And the examples that I'm showing for NLP applications are not necessarily applications that already do that. In fact, I don't think they're explicitly doing that. I want to motivate why it's important to work on these tasks. So counterfactual reasoning can be used for argument mining. So we can make an argument against claim X if we suggest that if X would have happened, that would result in an unwanted outcome Y. Here's an example from a data set that was debating the one-child policy in China. It's from a few years ago. And then one of the arguments against this policy was that if for any reason the single child is unable to care for their older adult relatives, the oldest generations would face a lack of resources and necessities. So that's counterfactual reasoning. Here's another very similar application, combating misinformation. Combating misinformation or misinformation detection. If you want to prove that claim X is false, you can show that if X was true, then it would entail claim Y, which is known to be false or agreed upon to be false. So here I just searched Twitter for face masks reduce oxygen, which is something that some people claimed in the beginning of the pandemic, or maybe some people still claim. And then I found this gem that says, if this was true, then all doctors and nurses doing 12-hour shifts for 6 days a week would be dropping like flies from wearing masks all day. Do some real research and stop spreading misinformation. So that's really nice. It's counterfactual reasoning in the wild. The task that we actually worked on is in the time travel data set, which is also based on the rock stories corpus. So here, there's a 5-sentence story. For example, Lisa was throwing a Halloween party. All her friends were dressing up. Lisa thought about being a wizard. Then she decided on a scarier costume. Lisa dressed up like a vampire. And then the beginning of the story, the second sentence of the story is changed with a counterfactual condition. So instead of all her friends were dressing up, now we have the sentence, it was a Game of Thrones themed party. And then the goal for the model is to predict an ending, a new ending, that on the one hand adheres to the counterfactual beginning. So it has to do to be related in some way, in this case, to Game of Thrones, and not to be related to all her friends were dressing up. But on the other hand, it only minimally edits the original ending, which is kind of like how you want. I mean, it's, I don't know the exact definition, but it's in counterfactual reasoning, you only want relevant things to change in the environment and not everything to change. And so here's an example of what the model that we developed predicted. Lisa thought about how she would dress up as a Lannister, but she didn't want to look like a Lannister. She wanted to look like a Stark. Lisa dressed up like a Stark. So you can see that there's a lot of similarity. A lot of the content is copied directly from the original story, but also there are some references to Game of Thrones that didn't appear in the original ending. Again, this is the same model that I skipped, and I'm happy to talk about it if we have time later. So this is a recap about everything we talked about today, and in pretty good timing. So first, we talked about benchmarks, which are used to measure progress on common sense reasoning research. They cover different types of knowledge and different modes of reasoning. But we still have this problem where we have this trade-off between models that are tasks that are easy to evaluate versus tasks that are really hard to game, and really, getting good performance on these tasks is a good indication that the model actually gained that capability that we're testing, and not just, finding correlations between spurious correlations between the inputs and outputs. Then we talked about symbolic knowledge. We talked about the knowledge bases that are used for completing missing or unstated knowledge that is very prevalent in language. But we also mentioned some of the disadvantages, how they have some insufficient coverage, especially in some domains. If we want to collect more common sense knowledge bases, it's not necessarily trivial to do that. And eventually, when we do have that knowledge, how do we incorporate it into models? Then we talked about neural representations, about how they are better than purely symbolic models because they are more generalizable. And I don't think I mentioned that, but I want to mention that it's much easier to train or to develop NLP models today than it used to be. I know it's like something that old people always say, oh, in my time it was harder, but really, even like in a matter of a few years, looking back, it used to be much more difficult. Now it's really easy. There are a lot of because there's so many people working on these topics, there are a lot of tools and models that are just very easy to use. So that's definitely good. But again, we are kind of like aware of all these challenges and all these disadvantages of neural representations, especially that they're a bit fuzzy and inaccurate when dealing with knowledge, and all these things like when they're not handling negation well, and stuff like that. Still, we don't really have a perfect solution, but we also talked about combining, putting everything together and building these reasoning engines that combine the symbolic knowledge with the neural representations. That's somewhat helpful. In terms of reasoning, we really only scratched the surface in what we talked about. There are very few models that actually do explicit reasoning in NLP in general, and in common sense reasoning in particular. To make some advancements, we need to improve the knowledge that we work with. We need to improve the methods that we're using. And we talked about neurosymbolic models in which the model was neural and the knowledge was symbolic. I think we also need to work on incorporating symbolic computation. Like I can think of an example for something that people actually did in NLI, where they had a model that was enforcing transitivity constraints. So if if the premise entails the hypothesis and the hypothesis entails the second hypothesis, then the first premise entails the second hypothesis as well. It sounds trivial. It's not so trivial to incorporate these kind of things into models, because language is much less logical and much more fuzzy and messy. But I think it could be. I think it's a promising direction, and we need to study more reasoning modes. And I see that I left it out from the recap slide as well, but yeah, we need to work on multimodal reasoning as well, as was mentioned here in one of the questions earlier. I think that's it. I have a lot of time for questions, so happy to answer any questions.